So the questions. Okay, 14. So here's the review, and yeah, we'll do that, Enrique. Just remember, I tried to get problems of every nature in these reviews, and on the help session, something could be missing, but you're guaranteed to hit everything if you look at all the quizzes and homework and in-class problems. So that's all wide open to get the exam. It's going to be problem-based, just like before. Okay? So we have a request to do 58 here, right off the bat. Which, if any reaction, would almost go to product at equilibrium. These conceptual questions are good because, man, either you know them or you don't, and they're quick points that you lose on exams. So these are good to know. How are you supposed to tell? With that Kc. And if you want to go to product, all at product, that means you want Kc to be really what? Big. So the answer would be A, 10 to the 113th. Right? You want Kc to be huge. Okay. Well, let's just pick on somebody to get us started here. Audrey, what type of problems did you really have the most trouble with? And we can just jump right into that one. Or if you want to start right at the beginning, fine. Start at the beginning? Okay, so I'm not going to let you off that easy. What's the answer to 56 then? Products over reactants. Don't include solids and liquids, so don't include this guy. There's no liquids. And everything needs to be in concentrations, in brackets, raised to their stoichiometric powers. So pretty much there's just two of them, right? H2O and CO2. Just be a bracket. There's nothing, right? How about 32? Steph. Does that look right, Enrique? pH 3? Yeah. Yeah, because she remembered to take off the plus, too, because you had to take away an H+. Okay. How about the products of the below reaction? Alyssa, let's just tell me the products first. Would it be HF? So, yeah, this is coming from that homework where they wanted what acid-base pairs started with a C? Conjugate acid-base pairs. And you're supposed to look at these guys and identify, oh, acting like an acid or a base. And you always start with the guy that doesn't have a choice. So by writing HF here, does everybody agree with this? Because F- can only act like a base. So it makes a lot of sense to write HF over here. And you have to add an H+ to it. So H+ and F-, just HF. Right? You can write the plus and minus up there if you want, but you don't need to. So this is a good starting point. So what would be the other product then, Andrea? What would be the other the SO4, okay? Because you rip this H, and you're just ripping it off and going over here. Just don't forget the charge. What does the charge have to be? See, it's kind of hard to see. It is a negative right now. It's going to be -2 because you got to take away an H plus. Take away kind of like take away a plus or add a negative, same thing. And we kind of recognize sulfate. Sulfate had a -2 charge. Okay. I don't know if you remember the name of this guy. He was hydrogen sulfate. That's supposed to, I don't know if you see it. There's a minus charge there. Okay. Mia, circle the acid that is stronger. So let's say you, okay, hang on, I'm gonna kind of try to screw you up here first. So you're sitting there on the exam, and you're trying to find these guys where? Oh yeah, let's say you're doing it wrong. That's the right way to do it. Let's say you're gonna do it wrong. You're staring at it where to find the answer here? At the chart. Right? So you're looking, I'm trying to get Mia to say the wrong answer. So she's looking at the chart forever and ever and ever, and she can't find these. That means the answer is on the periodic table. Okay, great. So Mia, which one is stronger?
I'm going to go with the H2.
Because
It's bigger?
Yes. The charge is distributed more. It's going to be a weaker bond. It's going to fall off easier. They both have 2 hydrogens, so that's not going to help. I bet you this guy's hydrogen sulfide is in the table, but I bet you that tellurium one isn't. Okay. Jose, how about 54? There's an easy one and a hard one. One of them is 0.045. Which one? The H3O. Because we never write this, Jose. We always write what ion? H with a plus, right? Because these two are exactly the same. Hydronium and H plus, they're exactly the same. So in the homework, they commonly threw one in with the other one. So which one is 0.045? Kendall, which one's 0.045? The H plus. And then if you write this, you're going to lose a point. Because what's missing, Megan? The big M. Good. All right. And then how would you get, or Bowdy, just give me an answer. The hydroxide.
I got
2.22 times 10 to the negative 13. Okay. So to get that answer, she probably, Audrey, well, I'm picking on you again. Connor, she probably did what? By, exactly. Divide 1 times 10 to the negative 14 by 0.045, and she got that answer. Perfect. Okay. Kenneth, 77. What's the answer?
Well, first, you get pH, you get the concentration of hydrogen by taking 10 to the negative 11.63.
Great. Which is going to be what number?
2.344 times 10 to the negative 12.
2.34 times 10 to the negative 12. Excellent. And then, because remember all you're getting in this equation sheet is pH is negative log of hydrogen ion concentration. You have to know the expression that Kenneth just told you. Hydrogen ion is equal to 10 to the negative pH. Or hydroxide is equal to 10 to the negative POH. That's also a game you could play. Okay. So the hydroxide ion concentration Steph, how would you get the hydroxide ion concentration now?
Well, when I did it, I used the pH to find the pOH.
I like Steph's way. Did you hear what she said? She used the pH to get the pOH. It's much less plugging in the calculator. This whole 1 times 10 negative 14 stuff, that's a lot of buttons to push, right? So what she did is she found pOH and did this. I like that idea. That's how I actually would have done it. Because you take 14 minus 11.63, right? Make it negative, put it to the 10 power, and you have your answer. What did you get?
I got 4.27 times 10 to the negative 3.
Oh, I mean, oh yeah, okay, 4.27 times 10 to the negative 3. And the other option was, right, divide 1 times 10 to the negative 14 by the 2.34 times 10 to the negative 12. Both of them would have worked. Oh, Enrique, you lucky guy. Do you remember these? These were confusing. And since they're confusing, I can pretty much guarantee they're going to be on the exam because they're so bloody confusing. All right. What are the general temperature and pressure conditions? Now let me set this up first. So we get temp. It could be high, high, low, or doesn't matter, I guess you could say. For pressure, same idea. High, low, doesn't matter. Okay, so Enrique, you just messed with the temperature one. What's the answer?
I don't know. I was going to ask you.
Okay. Well, let me ask you this then. Would you write heat as a reactant or product?
Product.
How are you supposed to tell? It's at the end with that delta H. And you're supposed to tell by looking at its sign. Since it's positive, it is a, anybody help them? Reactant. Positive means it has to be reactant. Think of it this way. If it's negative, you've got to be losing this heat. And if you're losing it, it's got to be a product because you're producing it. So that's how I remember this. If it's negative, man, I'm losing all this energy. It's negative. I'm losing all this energy, and it's just going away, right out into the air. So heat's a product. But it's positive, so heat is over here. You have to use that Le Chatelier idea here, Alyssa, to finish this. What's the answer regarding temperature? I pretty much got to do the experiment in my head. I crank up the temp and see what the effect is, and then I give the appropriate answer. And you want optimum production of nitrogen gas. So this is the guy that you want a lot of. Crank up the heat, then you've got too much reactant. So it shifts to product, and nitrogen's a product. Excellent. So you should crank up the heat, so that means make it high. Alrighty. Andrea, this is I think the more ugly one even. The pressure. What's the answer? You don't know? Okay, there was a game plan for this. The game plan was figure out the number of what molecules on each side. Someone said it. Gas. Figure out the number of gas molecules on each side. And how you figure that out? You just add up the stoichiometric coefficients for anything that has a G as a subscript. Right? Add them all up. And if it's higher, if you have more gas on one side, you can kind of think of that as the high pressure side or something. Where if you have more gas on that side, that's the side that wants a lot of pressure. Right? So kind of think of it, well, let's just, maybe it's easier just to do the logic. and just start it. How many gas molecules, everybody, over here? Does everyone agree there's 4 gas molecules? How many on this side? 3. And I think how my brain handles it, I just do the experiment in my head, Mia. I just crank up the pressure. Just like with heat, I crank up the heat and see what happens. So if I crank up the pressure, so right now it's hunky-dory, it's at equilibrium. But somehow I crank up the pressure, put a piston on there or something. I change the conditions. The system wants to respond to generate more pressure or relieve the pressure. If I'm putting this piston on there, the system wants to respond to generate more pressure or relieve that pressure. Relieve it, right? Does that make sense? It wants to relieve it. You're pushing on it. It wants to relieve it. Okay. Is it going to relieve it by generating more gas molecules or fewer gas molecules? How is it going to relieve that pressure? If it goes to the side with more gas molecules, well, that's more pressure, isn't it? Because you have more gas. So it's going to go to the side with less gas molecules. That's always the effect of cranking up the pressure. If you've got the same number of gas molecules on each side, then it's a trick question. It doesn't matter because it's not going to do anything because it can't shift. Okay, so you crank up the pressure. It's going to shift towards products or reactants. Products is what we want a product. Yeah, so you want to do that. Crank up the pressure then. Crank up that pressure. Because then it'll shift to relieve that pressure. It definitely won't shift to reactants because then it's going to create even more pressure. That's just the opposite of what nature does. Okay. Then we had these equilibrium composition problems, Jose. Yeah, Enrique.
What would the heat not matter?
Oh, when would the heat not matter? That's a good one. Man, the only way to make that a trick question, where it says the heat doesn't matter, is I would have to change this, anybody, to what? 0. Change it to 0. Or 0.0002. That's 0. Okay. These equilibrium composition problems, Jose. What is the composition of the equilibrium mixture? And there's all these answers there. I told you the answers are the moles of each one. How do you do this? How do you get these answers, this equilibrium composition? How the heck did we do that? Do you remember? He doesn't remember. Anybody remember? We made an ice table. Now, in these, remember there are 2 ways to make these ice tables. You could make, in the ice table, you could put moles or you could put molarity. Now, here, they don't even mention liters, so why even mess with it, right? You're just going to make a mole table. So you do ice. Let's see here. Make some space. So we're supposed to do ICE. Kendall, they want the equilibrium composition. That equilibrium composition is always what row? What row? The E row is all the answers all the time. Always. Okay. So we got to fill this out, Andromeda. What are you going to put in this table? Now let me try to confuse you. Do I multiply it by 2? Because there's 2 SO2s.
You subtract 3.
Do I subtract from 2? Right? You're doing so good. I'm just trying to instill some confusion here, because that's what's going to happen. You're all nervous about taking the exam.
The 2x.
Yeah, the 2 comes into the change row. Exactly. That's the only place you care. The 2 comes into the change row. The 2 comes into place if you have to write an equilibrium constant expression, because that means you got to square it, that concentration. But if the initial is 0.0524, just like you said.
And it's an NG2.
Oh, thank you. Okay, and then anything else on the initial row? Oh yeah, the O2. And then if you wrote zeros or dashes, but I just like to write dashes and have to look at it. So the change row, Kendall got you started there, Megan.
So it's minus x.
Minus x for the other guy,
And plus 2.
and positive 2x. Okay, now Kendall said that the E row was all the answers. How do you get it?
Just bring it down.
So the first one would be,
0.0524 minus 2x.
yeah, add them up. 0.0262. Okay. Then, Bowdy, what did you do? Solve for x.
Does it give you the 0.0311 mole?
Yeah.
That's how you solve for x. Exactly. Solve for x. So you set what equal to 0.0311? 2x. And then you got it. Then it's just straightforward after that. Solve for them, substitute them all in, you get those numbers. You place, here's another one. Read this one over. Okay, Kenneth, what are the equilibrium concentrations? Before we ask for equilibrium composition, is that the same question?
I don't think it is.
No? When they say equilibrium concentrations, equilibrium composition, it means means you need molarity, but it's a little better than saying equilibrium composition, because they're telling you what units they want you to give the equilibrium composition in. But it's the exact same question. At equilibrium, how much do you have of everything? So they don't want the answer in moles, though. They want the answer in what Bowdy said, molarity, concentration. Which is what over what again, Steph? Moles over liters. So it would probably make the most sense, Audrey, to make a what type of ice table then? Since they're after concentrations, make a what? Make a molarity ice table. I mean, you could do it with moles. You'll get the right answer, but it's all going to be in moles. Okay, so make a molarity ice table. What is this? Hints below. What is this? I forget what this is. Oh, this is going to turn into one of these. We should set this up, right? It turns into one of those quadratic formula problems. We should definitely set this up. Okay.
How do we know exactly when to make it a quadratic formula?
Exactly. So I think what you do is, see, I don't have any of this stuff memorized. So when I hit it, that's when I solve it. So in other words, I don't imagine it's coming until I actually see it happening. So let's just take one step at a time and see where it leads you, right? And I think what's going to happen is before we got the equilibrium concentrations, because they told us one of the answers, right? At equilibrium, they said what the SO3 was. See that? I think, Alyssa, that's the difference. When they don't say one of these, the equilibrium composition contains so many moles. So you know what one of the answers were in the E row. When it doesn't say that, you're going to think, oh, Smith, you gave me another quadratic formula problem, right? It has to be. So let's see if we can set it up. You set it up the exact same way. You get that E row, and then you substitute that E row concentration information into your Kc expression. There's your quadratic formula right there. You got to solve for x. Yes, I would. I would turn everything into molarity because you, yes, make a concentration table. Enrique, did you get this far with the ice table? Okay, but you can see how I got there, right? Okay, so let's say you got this far. What do you do now? Oh, let's back up. Let me ask you this question. They wanted to know the equilibrium concentrations. Again, where are all the answers? The E row. You just got to know what? What? You just got to know what x is, right? Okay. The other problems, they're going to give you what one of these is at equilibrium. Then you just solve for x. But they didn't here. So you know what's coming. You know it's got to be this quadratic formula question. Okay, Alyssa, how do you set this up?
34 equals,
There you go.
H2 over H2 bracket H2.
Oh, I like that she said this. Oh, sorry. Products over reactants.
Yeah, into H2.
Yeah. Because if you don't write this, it doesn't, see how long it's taking me? What is this, about 10 seconds? It takes about 10 seconds. Exactly, Alyssa, exactly right. But it takes about 10 seconds to do this. The quadratic formula problem, what, 10 minutes? You screw up writing this simple expression, you just wasted 10 minutes of time and effort. So write this expression. Because it's, odds are there's going to be 2's and stuff up here, and you make those exponents up here. Okay. Now you substitute everything in. Solve for x. I bet you that's what's under here. There it is. Okay. This would be a good practice one. Right? I don't think we should do it now. I think this is a good thing for you to practice on. Okay. See if you can get this to work out. Because I want to see if you can remember how to do this other stuff, because we haven't hit these other problems. Make sure that you can get this to work. Okay. How about this kind of thing? So we didn't hit on this in class. This is the last stuff we talked about, and we didn't talk about it. We've got about 10 minutes here. How would you do EX2? Andrea, it's a fun question here. We've got 0.8 grams of sodium hydroxide. They just massed it out, dumped it in 50 mils of water, and they want to know what the pH is. How the heck would you do this? Good. Turn that 0.8 grams of NaOH in 50 mils, turn it into molarity. That's a great idea. Now, if you do that, if you follow Andrea's advice, it's molarity of what, Mia? If you follow her advice, you turn it into molarity. That means somehow you get moles divided by liters. You now know the concentration of the NaOH. But it's confusing to say NaOH, because in that cheat sheet with all the equations, there's no NaOH anywhere. It's better just to say hydroxide. And why? Why? Yeah, so we can do all the calculations. But why is the concentration of NaOH equal to the concentration of OH? Which is equal to the concentration of Na, actually. Dissociates to what percent? Totally, 100%, because it's a strong base. Just like when you said, just like if we said you have 0.2 molar HCl, everybody knows, oh yeah, H plus is 0.2 molar. Because it's a strong acid, strong base. Those are the only ones we're messing with. So get the moles divided by the liters, you get the hydroxide, and then it's just like a regular homework question, right? So remember how to get grams to moles? You had to calculate what, Cameron? What was it called? Molar mass of NaOH. How about, so see if you can get that one. EX3, at least you got a game plan for EX2, so you can give it a shot and you get stuck, ask at the help session. EX3, read over EX3 and see if you can give me an idea of what to do here. Jose, how the heck are you going to do EX3? Do we add the concentrations? There's a good question. Because if we know the concentration, they're both HCl, right? And if you know the concentration of H plus, just take the negative log of it and you got your answer. Can we add the 0.9 and the 0.5? That's a good question. No, we can't.
So we just find the pH of both of them.
But we can add what? No, you can't add the pH of both. We can add what? You can't add concentrations, but you can add liters and get total liters. You can add moles and get total moles, but you can't add concentrations. It's like saying I've got a really concentrated solution of this. You know its concentration. I got a really dilute solution of this. I dump them together and I know the answer? I don't think so. It's really complicated. You got to know how much is in each one, add the moles together. You got to know the volume of each one, add those together, divide the two, then you know the concentration of the mixture. I wish life was as easy as adding 0.9 and 0.5, but it's not. So good. And this answer, right? Get the total moles of H plus. Get the total liters. then divide them, because then you'll have the concentration. Then divide the two. That one divided by this one. Then you can get POH. You can get whatever they want. Okay. Getting the total liters I don't think is bad. But Kendall, do you remember how to get moles? If I look at one of these, big M equals, there you go, and solve for what you want. Exactly. Big M is going to be the 0.9. The liters is going to be 0.25. Solve for moles. Do the same thing for this one. Okay. So now you got a game plan for EX3. Give it a shot. If you get stuck, we'll help you out at the help session. Last one. Last one. Again, we didn't have time to hit on this in class, but you have all the tools you need. And no worries. What do we have here? We've got, Megan's going to tell us. You've got 0.8 grams of barium hydroxide added to 30 mils of water. What will be the pH of the solution? How are you going to do this? Oh, good. You could find POH and subtract from 14. So if you find POH, that means you first got to find what? Because POH is negative log of concentration of OH. So she says she wants to use this equation, right? She wants to use that because then pH plus POH is 4. She can get that. Connor, that sounds like a game plan. I like it. How are you going to get this then? How are you going to get it? We got to get concentration of hydroxide. Now before we had, where did it go? Before we had this guy, right? And you guys saw, I think, how to go from this to get moles of hydroxide, right? You have to use molar mass. Wouldn't it be the same story here? Except you got two OHs. That's just the trick. So you take your 0.8 grams of barium hydroxide, and don't forget what Enrique said. Realize you have two OHs. So get the molar mass of the stuff. That's always molar mass, right? 1 mole of the stuff is that many grams. You always do it that way. Just realize, though, you're after moles of OH. So like what Enrique said, don't forget you have two OHs. You could just take your answer times 2 here, or actually show your work. And 1 mole of barium hydroxide, so these units cancel. I have how many moles of OH? 2. There you go. So that concentration of hydroxide is just moles over liters. And you already got the top part. Okay. So try those. If you have problems, just ask at the help session. We can work a gazillion of these things. Or come by the office. So we're about out of time.